Okay, this is part 2 of the projectile problems video, and here's a second sample problem. I'm going to make it a little bit tougher this time. Let's say we have a target shooter who's up on top of a cliff, and then the target shooter is going to aim the rifle down at 20-degree angle below horizontal, and the muzzle velocity of the bullet coming out of the barrel, let's say, is 500 meters per second. And we want to find one thing. Let's say that it's 50 meters. The cliff is 50 meters high, and we'd like to find out the range. Okay, so let's just imagine be traveling. So we want to find the range here. So that'd be delta x, right? And we also want to find this time the final velocity v2. And remember, that's a vector, so that also includes the angle here. Okay, so that's our problem. Shooting a gun from a cliff at a target down below. The cliff is 50 meters high. The angle is 20 degrees below the horizontal that the gun is aimed, and we want to find out what the range is right here, and we also want to find out what the final velocity is. And remember, vector nature of it, it includes the angle. Remember, we have to deal with Galileo's equations here, and this time we don't have a total displacement of 0, do we? What is the displacement in this case? Well, it's starting up here and it's going downward. I'm going to define down as positive in this example, since all of these quantities vertically are pointing downward, including gravity. So that means I don't have to deal with negative signs or anything. So delta y in this case would be equal to a positive 50 meters. Gravity, the acceleration in the y direction, would be a positive 9.8 meters per second squared. Okay? And even the downward component of the velocity vector would be positive too. Let's find the components of the velocity. Here's the vertical component. We'll call it Vy1. And then the horizontal component would be Vx1. Okay? So we'll just use our trig and go from there. So Vy1 would be equal to the hypotenuse of 500 times the sine of 20 degrees. So 20 sine times 500, and that gives 171 meters per second. Now, since we're defining down as positive, I can make this a positive 171 meters per second for the starting velocity in the y direction. Starting velocity in the x direction, we use the same principle. We'll take our angle of 20 degrees, take the cosine of it, times the 500 meters per second, and that we get about 470 meters per second. Okay, so we have the starting velocity in both the x direction and the y direction. That's very important. We need to use those. Everything downward is positive, so that makes it a little more straightforward. Okay, well, let's say we want to find the final velocity. Okay, well, we know what the starting velocity is, but we don't know what t is. That wouldn't work. But this one, I mean, it wouldn't work as is in one step. But this one here would allow us to get that. So what information should we use? Well, we have more information in the y direction, so let's use it in the y direction. So this would be Vy2 squared minus Vy1 squared equals 2 times acceleration in the y direction times delta y. Now we know what delta y is. That's 50. I can plug that right in there. We know the acceleration due to gravity is 9.8. They're both positive, right? And then we have a 2. We know that Vy1 is 171 meters per second. That's going to be squared, so minus 171 squared. And then Vy2, we don't know what that is. We can solve for that. So if we just go ahead and solve real quick for that. So we get 980 over here, and over on this side. I'm sorry I split it up, but I felt maybe somebody might get lost if I don't. So 171 squared. So this is Vy2 minus 29,241. Okay, so that's what we have so far. I'll add 29,241 to both sides. We get Vy2 is equal to Vy squared, excuse me. No wonder it was coming out so big. Vy squared is equal to 30,221. If I take the square root of both sides, we're going to get 173. There we go. So Vy2 is equal to the square root of that, which is about 174 meters per second. Okay, so that's the final velocity, but that's just in the y direction. So that would be this component right here in purple. Vy2 is pointing downward like that. Okay, guess what Vx2 is, going horizontally? Well, it's going to be the same as this one. In fact, with projectile problems with no air resistance, since there's no horizontal force acting, it's going to be the same horizontal velocity the whole time. So Vx2 would be equal to Vx1, that's 470 meters per second. And so we have both components now. We know this is 174, and we know this is 470. So 470 here, 174 here. We can find the angle, and we can use Pythagorean theorem to find the final velocity. So if we use the Pythagorean theorem here, we'll say the final velocity v2, the magnitude at least, is equal to the square root of our 470 squared plus our 174 squared. Just solving for that as quickly as I can. Okay, we'll get 470 squared plus quantity of 174 squared. Okay, now we'll be sure to take the square root of both sides, and we get 501. Wow, it picked up some speed. So 501 meters per second for the final velocity, the magnitude of the final velocity. Okay, let's get the angle. Well, to find the angle, we can use the inverse tan function of, remember, tan is opposite over adjacent, so that would be 174 over 470, and that gives us, take the inverse tan of that, 20.3 degrees. Now that's a reference angle. So it's just a coincidence that it's almost the same angle as that one. But this angle here is, it turns out, 20.3 degrees. Just a coincidence. But anyway, so that's the angle. If we wanted to put it in polar form, the final velocity v2 would be equal to 501 meters per second, comma, at 20.3 degrees with reference to the ground. Okay, so that's how to find the velocity at the end. If we want to find the range, that's not too much of a problem either, is it? Because we can use the same formula if you want, and there are many ways to do this. If we want to find the range, delta x, we could either use this one here, but we don't know the time, or we could use this one again. So I'll use that one. So, but on the x direction. So v2x squared minus v1. There's going to be a problem here. We can't use it because there's no acceleration. So that's kind of a ridiculous thing. I did this on purpose to show you that you can't just use these formulas blindly. In the x direction, the acceleration is 0. The velocity at the end is the same in the x direction as at the beginning, so 0 equals 0, not helpful. Not helpful at all. So what we're going to have to do then is we're going to have to solve for time first. Okay? So let's solve for time. Let's use the first equation up here. We have v2 in the x direction. In the y direction. We have to use the y. Okay, v2 in the y direction equals v1 in the y direction plus ayt. Now we can solve for y. v2 in the y direction, we remember, was 174. I plugged that right in here. Equals v1 in the y direction. We're just using components now. That was 171. Okay, times, plus 9.8, which is the gravity and the acceleration in the y direction, times t. Now we'll go ahead and solve for t. Okay, that'd be about 174 minus 171 is 3. 3 over 9.8, and that gives us 0.31 seconds. So 0.31 seconds, that's the time. Now it didn't ask for time. However, we kind of need that in order to solve for the range. Now to get the range, we can then substitute. We can just go ahead and use the second equation up here and just plug in. The range then would be equal to v1 in the x direction times the time, and then plus 1/2 axt squared. But remember, in the x direction, the acceleration is 0, so we just end up with this. We can substitute that in for time, and we'll get the range. So x is equal to vx1, which is our x component of 470 up here, times the time that we just found out of 0.31 seconds. So we get 0.31 times 470, and we get 145.7. So 145.7 meters is the range. Okay, so there we have it. Thanks, everybody.